This video is about Kirchhoff's rules. These are rules that we use, or laws that will be used interchangeably in the video. They are laws or rules that are used to help us analyze circuits. So the very first part of Kirchhoff's rules is the junction rule. And the junction rule has to deal with, you guess it, junctions in a circuit. So what is a junction? Well, a junction is a place in the circuit that is sort of like a fork in the road for the voltage. So right here, our current can go this way, or it can branch off and go that way. So Kirchhoff's junction rule says that the sum of the current entering a junction equals the sum of the current leaving a junction. So we will see here, we have I1, current 1, going in to this junction. And then it's going to split off and go this way. So we're going to call that I2. And then we'll have it split off here and go this way, and we'll call that I3. Well, when it gets to right here, the currents are going to rejoin and they're going to leave as a current, because current is just like energy. As far as, it's going to have to be conserved. It's not going to get lost somewhere in the current. So what we have happening here is the sum of the current entering junction A, right? Entering this junction is I1. And that equals the sum of the current leaving, which is I2, plus I3. And we'll call this junction B. And then for, let's see, call this A, do B over here. Okay, and then for B, we have the sum of the currents going in is I2 and I3. So we have I2 plus I3 equals the sum of the current leaving the junction of B, which is going to be I4. And that's it. That's it for the junction rule. It's pretty straightforward, right? All right, so then we're going to look at the loop rule. So whereas the junction rule told us about what the current is doing, the loop rule is going to help us understand what the voltage is doing, and then how that relates to current, and how we can end up finding, all kinds of really cool things. Okay, so the loop rule says that if we add all the voltage used or given by each element in a circuit in a closed loop, they sum to be 0. All right, so what is a closed loop? Well, each of these sections is considered a closed loop. Now, before you can decide really what and how your closed loops are going to be, the first thing you have to do is label your currents and your junctions. So we have a junction here, and we have a junction here. And I'm going to say that this is I1, and I'm going to say that this is I2, and then I'm going to say that this is I3, and then I'll call this one I4. Okay. All right, so we have labeled our currents going out and going into our junctions. Now, when you're doing a closed loop, that just has to be somewhere here, and we also have to where we could do a loop that's going around here. I'm only going to focus on these two loops. And so we'll have up here is going to be what we'll call loop 1. And then down here, we'll have a clockwise loop as well, called loop 2. Okay, now the reason that we do this is because it allows us to follow this rule that says if we add all the voltage used or given by each element in a circuit, they sum to be 0. Now that means that some of these things are going to have negative values and some will be positive, because you can't have all positive values and get to 0. If you had all positive values, you would never hit 0. So if the loop, according to Kirchhoff's rule, if the loop is pointing in the same direction as the current, then it's going to be a negative voltage, or we're going to subtract the voltage. If the loop is going in the opposite direction, like down here, if it's going in the opposite direction of the current, then we would add that current through specific resistors or things that we come upon. So what we're going to do here is I'm going to show you really quickly how this works. Okay, so for L1, it's going to equal 0. They're all going to sum to 0. And this is how we're going to analyze the circuit. I start up here. Always, I find that consistency is very important in physics and in math. So I start here all the time, and I always use a clockwise loop. You could use counterclockwise if you like, but I like to do the same things. So see which one works for you in your practice. Okay, so I'm going to start right here, and we're going to come to an R3, which is a 3 ohm resistor. And because this is going in the same direction as our loop, we're going to subtract this voltage. So minus VR3. Then we come to a 1 ohm resistor, also with that current going through it in the same direction as the loop. So we're going to say minus V, oh, I got 2 minuses there, minus VR4. Okay, and then we're going to keep going, and we don't pass anything here, and then we get to this junction right here, which is R2. It's a 2 ohm resistor. Now the loop is going in the opposite direction of our current, because this current is pointing towards our blue junction here, and our loop is pointing in the direction of the red junction. So when it's in the opposite direction, we're going to add it. So it's going to be plus VR2. Then we're going to keep going down here, and we come to another resistor, and this is a 1 ohm resistor going in the opposite direction. Our current is flowing the opposite direction of the loop, so we're going to add it. Okay. And then we keep going around, and we've come back to where we started, so we have completely analyzed this loop. That loop is done. Now let's look at how this would look for the second loop. So if we start right here again, we're going to start and we're going to run straight into this 1 ohm R1 resistor. This time our current is flowing in the same direction as our loop. So we're going to be subtracting VR1. And we continue along this line, and we now run into the 2 ohm resistor where the current is still flowing in the same direction as our loop. So we're going to add VR2. Or excuse me, subtract VR2. Okay, then we're going to keep going around, down, nothing's happening. Well, what happens when we get to a battery? So this isn't a resistor, this is the battery. Now this has nothing to do with how the current is flowing in regards to how the loop is flowing. This has entirely to do only with the loop. So as we're going around the circuit, if the loop is pointing to the short end of the battery, which it is here, the negative end of the battery, then we're going to be adding the voltage, which let's make this 9 volts. Then we're going to add this voltage. So let's say plus 9 volts. Okay. And if it were coming to, say it was going this way, say I had drawn it counterclockwise, I would have had the loop pointing at the positive end, so I would have subtracted the voltage. And we'll see when I do a full problem on this, you'll understand why it doesn't really matter which way you choose. You just need to be consistent and make sure you follow the laws of setting it up with the current going, where the sum of the current entering a junction equals the sum of the current going out. All right, so then we go around here and we've come back to where we started, so we have completely finished analyzing that loop. And in the next video, I'm going to go over how to use these laws to help us to find certain aspects like missing voltages and missing currents using systems of equations with these laws. And these laws are how we get these equations. You'll see how just by going around these loops we were able to get this information out, which we're then able to plug in to get the current through each element of our circuit. All right, I hope this was helpful.